Welcome to Math with Professor V. This is video lecture for section 6.1 for business calculus on absolute extrema. Now we've talked about relative extrema in the previous unit, and now we're going to look at a similar but different concept regarding absolute extrema. So first, let's get some definitions under our belt. Let f be a function defined on some interval, and let c be a number in the interval. Then f of c is the absolute maximum of f on the interval if f of x is less than or equal to f of c. So basically, c is the x value that yields that absolute max value, f of c. And this is the greatest function value, or y value. All function values are less than or equal to f of c on that interval. Similarly, if for every x in the interval, we have f of c less than or equal to f of x, then we say f of c is the absolute minimum of f on that interval. So different from relative or local extrema, an absolute max or an absolute min is the singular largest function value or smallest function value on an interval, and it also could be the endpoint of an interval. First, let's look at a couple graphs to make sure visually we're able to identify where we have an absolute max or an absolute min. So first example, f of x. Does it have an absolute minimum? Yes, right here. We have an absolute min at x1. And if someone actually wanted the absolute min value, you would say f of x1 is the absolute min. Now, x1 also yields a local min, just like x3 does, but only f of x1 is the absolute min. This function value is smaller than the function value here. Also notice our derivative is 0 here, because if I drew a tangent line, its slope would be 0. So f prime of x1 is 0. That means x1 is a critical number. All right, is there an absolute max? No, there is not. This is a local max, right? x2 yields a local max or relative max, f of x2. But there is no absolute max. I'm not restricting to a particular interval, and this function goes up forever. So there is no absolute max. Okay, let's look at this next example. Is there an absolute min? Yeah, all the way over here at this endpoint. So absolute min, again, is at x1. Is there an absolute max? This time, yes. Look, the absolute max is right there. And it occurs at x2. Are both x1 and x2 critical numbers? x1 is not, x2 is, right? Slope of the tangent line there is 0, so this is a critical number. F prime of x2 is 0. All right, good. So now we're going to look at the extreme value theorem, which tells us something very important for many of these applications that we're going to look at in this course. So a function f that is continuous on a, and here's the key, closed interval from a to b will have both an absolute maximum and absolute minimum on the interval. So I want to go back to the first example that we looked at and see why it failed the extreme value theorem. The function has to be continuous on a closed interval, and then we are guaranteed it has both an absolute max and an absolute min. And if you look here at this first example, the problem is not continuity. No, my function's continuous. It's that I'm not looking at a closed interval. I was looking at the entire domain of the function, which was all real numbers. That's not a closed interval. But if I were to come along and say, okay, we're going to restrict the graph to this interval. Here's A, here's B. Then for sure, I would be able to find an absolute min and an absolute max on the interval. If I imposed this restriction, this would still be my absolute min, And then depending on if the function value is higher at x2 or here, then one of those would yield my absolute max. So the extreme value theorem is very useful because we know we're guaranteed both an absolute max and min so long as we're looking at a continuous function on a closed interval. Okay, so here's the process, how we're going to find the absolute extrema. You're going to be given the function, you're going to be given the interval. You start off by finding the critical numbers for f on the open interval from a to b. So remember, you take the derivative f prime of x, set it equal to 0, and also find where it doesn't exist. That's how we get our critical numbers. Then you're going to evaluate the function at all of those critical numbers. So you don't need to make the number line and do the first derivative test. You're just going to take all those critical numbers, plug them in the function. Then you also evaluate f at the endpoints of the interval a and b. And then you just compare everything. I like to put it in a table. You do you. The largest value is your absolute max, and then the smallest value is the absolute min. It's a pretty straightforward process. I think you'll like it. Most of my students like it quite a bit compared to everything else, you know. Okay, so find the absolute extrema if they exist, as well as all values of x where they occur. So they want the x values and the y values. Here we go. First one, f of x is x cubed minus 3x squared minus 24x plus 5, and we're on the interval from -3 to 6. So starting off, we need our critical numbers. Let's take a derivative. Look at this non-threatening polynomial. I love it. So we've got 3x squared minus 6x minus 24. So to find our critical numbers, I'm going to set the derivative equal to 0 and see where it doesn't exist. I already know there aren't going to be anywhere it doesn't exist because it's a lovely little polynomial. So let's just take 3x squared minus 6x minus 24, set it to 0. I can divide everything by 3, so then it's x squared minus 2x minus 8 is 0. And then this will factor into x minus 4 times x plus 2 is 0. So I have two critical numbers, namely positive 4 and negative 2. So I need to evaluate f, the original function, at each of these critical numbers. And I also need to evaluate f at the endpoints of the interval that we're given. So this is where I like to make a table. X, f of x. You put your critical numbers on there. So 4, negative 2, and then you put the endpoints of the interval, -3, 6. So these are the critical numbers. And then these are the endpoints. You can do it in whatever order, it doesn't matter, okay? And then I'll save you the stress. I plugged them all in ahead of time. So this will be -75, 33, 23, and -31. So then you just come through and you look at the y values. Which one's the smallest? This guy. Which one's the biggest? Correct again. So then we summarize. So absolute min, I would just write it like this, f of 4, which is -75. Then you've, found the x values and the extreme values, x and y. We're given everything to the people. And then the absolute max, that's right, f of -2, which is 33. Bada bing, bada boom. Let's box it. That's the final answer. Good? Look at that. I mean, it's pretty relaxing. No number line, no stress, just critical values, endpoints on a table, bam. Let's try some more. F of x is x to the 4th minus 32x squared minus 7 on the interval from -5 to 6. So here we go. Let's take a derivative. So this is 4x cubed minus 64x. And then we need our critical numbers. So where f prime is 0 and where f prime doesn't exist. This is going to be none again. Set this derivative equal to 0. Now we got to factor with care. The greatest common factor is a 4x. So then I'm left with x squared minus 16. And then that factors more, doesn't it? X minus 4x plus 4. So I have three critical numbers this time. X equals 0 from that 4x out front, positive 4, and negative 4. And always make sure before you put them on the table, are they in the interval that was given? So 0, 4, negative 4. Yeah, those are all between -5 and 6. So they all get to go on the table, as well as -5 and 6. So there we go. Here's x, f of x. You put your 3 critical numbers, 0, 4, -4, and then the endpoints of the interval as well. So let's see. This is -7, -263, -263, -182, and 137. So absolute min, we actually have 2 places where it happens. Since they have the same y value, which is the smallest, we have more than one place where the absolute min occurs, okay? And then absolute max is right here. Okay, so absolute min, if you want to be efficient, you could do f of ±4, which is -263. And then absolute max, f of 6, which is 137. How was that one? Good. I wanted to show you that it is possible to have your absolute min or max occur at more than one place, okay? Good. Couple more, and this time we're going to have, more involved derivatives. You can't just deal with polynomials exclusively your entire math career, so sorry. Okay, f of x equals x over x squared plus 2 on the interval from 0 to 4. So here we go. We got to do the quotient rule, right? Hooray! Pretend you're excited. It'll help. So we've got low denominator, d high, minus numerator times derivative of the bottom over denominator squared. So what's this going to be? X squared plus 2 minus 2x squared over x squared plus 2 squared. Didn't need such an aggressively long fraction bar. Okay, beautiful. So then this is going to be what? Positive 2 minus x squared over x squared plus 2 squared. There's my derivative. Okay, perfect. So let's see where it's 0 and where it doesn't exist. So remember our little shortcut. The derivative 0 when the numerator is 0. So that means 2 minus x squared is 0, which means x squared is 2, which means x would be plus or minus square root of 2. But look at the original interval. It's only from 0 to 4, so no negative values, only positive. Rad 2 is on the interval, so that's the only one I'm going to consider. And then the derivative doesn't exist when the denominator is 0. So that would happen if x squared plus 2 is 0, which happens when x squared is -2, but that's not possible. That doesn't have any real solutions. So no critical values from there. So here's my one and only critical value I'm going to put on the table. And then what else goes on the table? Do you remember? Yes, the endpoints of the interval. So 0 and 4. So we've just got 3 numbers. Rad 2, 0, 4. Okay, so if you substitute in rad 2 into the original function, you'll have rad 2 over 4, which is about 0.3535. If you plug in 0, you get 0, and 4, you get 2/9, which is just 0.2 repeating, so 0.2222. So can you see which is the biggest and the smallest? Biggest, smallest, good. So absolute max, f of rad 2, which is rad 2 over 4, and then absolute min, good, f of 0, which is 0. Beautiful. How are you doing? Got one more example like this, and then we'll look at a econ application, okay? So f of x equals x plus 3x to the 2/3 on the interval from -10 to 1. Okay, so let's take the derivative. F prime of x is going to be 1 plus, now 3 times 2/3, the 3 is going to cancel. So then I just have 2x to the -1/3. And then I would clean it up, put that x to the negative 1/3 in the denominator. So this is 1 plus 2 over x to the 1/3. Let's just get a common denominator. So this 1 is going to be x to the 1/3 over x to the 1/3. And then we can write this as x to the 1/3 plus 2 over x to the 1/3. Good? There's my derivative. Okay, let's get our critical numbers. So I want to know where f prime of x is 0 and where f prime of x does not exist. So f prime of x is 0 when the numerator is 0. So I'm going to take x to the 1/3 plus 2, set it equal to 0. That means x to the 1/3 is negative 2. To get rid of the 1/3 exponent, you raise both sides to the third power. Remember, x to the 1/3, that's the same as cube root of x. So you just cube or raise both sides to the third. And then now I have x equals negative 8. Is that on the interval? From negative 10 to 1? Yeah, we're good. Okay. Boom. So there's a critical number. F prime of x does not exist when the denominator is 0. So that happens when x to the 1/3 is 0. So that happens if x is 0. Is that in the domain? Oh yeah, we're good. Negative 10 to 1 includes 0. Wow, okay. So x, f of x, remember always plug it in the original function. And then we've got negative 8, 0, negative 10, and 1. Cool. And these come out to 4, 0, 3.925 approximately, and 4. Okay, look at that. Absolute max happens twice. And then here's the absolute min. This is exciting. Okay, so absolute max, you could write it like this. F of negative 8, which equals f of 1, which is 4. And then absolute min, f of 0, which is 0. Okay, good. That was a nice one. Boom. All right, so let's move on. Last thing we're going to do is look at an economics example where we have to find absolute extrema. So a company has found that its weekly profit from the sale of X units of an auto part is given by the following function. Now, production bottlenecks limit the number of units that can be made per week to no more than 150, while a long-term contract requires that at least 50 units be made each week. Remember, X is the number of units. So this is telling me X has to be less than or equal to 50 and 150 and greater than or equal to 50. Find the number of units that must be sold each week to maximize profit, and then find the maximum weekly profit. So we're on a closed interval. We're on the interval from 50 to 150, and we want the absolute max profit. You see how this is a closed interval. Perfect. So we're going to just use the same process that we did for the previous examples, just now there's some context to it, okay? So first thing, yes, take a derivative. P prime of x is going to be negative 0.06 x squared plus 600. From here, we need our critical values. So P prime of x is 0. P prime of x doesn't exist. It's not going to have any values where it doesn't exist. It's a polynomial, but let's set it equal to 0. Negative 0.06 x squared plus 600 is 0. That means 0.06 x squared equals 600, which means x squared is equal to 10,000. So x is 100. Okay, that's my one and only critical number, because 100, yep, that's on the interval from 50 to 150. So now we're going to compare the profit values. So we have P of x, not F of x this time, be careful. So I'm putting 100 and then also the endpoints, 50 and 150. Again, I'm so kind. I plugged it in for you. So if you make 100 units, the profit is 20,000. If you make 50 units, the profit's 7,500. and 150, it's 2,500. So all we want is the absolute max. We don't care about the absolute min. And here it is. So our critical number indeed yielded the absolute max profit. So I would tell them sell 100 units each week for a max profit of $20,000. There you go. All right, how was this lesson? I think it's pretty straightforward, right? Hope you enjoyed it. Don't forget to give the video a thumbs up. Subscribe if you haven't already. And then I'll be following up with more video lectures for business calc shortly, very shortly. Also follow me on Instagram and TikTok, Math with Professor V. Thanks you guys so much for your support. I'll be back sooner than later. Bye-bye.